Now you can take it away.
Okay. All right. Thanks, David. So today I'll be talking about atmospheric rivers. As David said, I work here at UBC on the weather forecast research team. And I want to acknowledge that some of the material in this presentation was provided by Dr. Doug McCollar, who's my boss at BC Hydro. All right, so I thought I'd start off giving a bit of an introduction about myself. I'm from the Northeast, originally from New York State. I did my undergrad at the University at Albany. And I also spent some time at Mount Washington Observatory as an intern and as an observer. And that got me interested in mountain meteorology. And so then I pursued that at University of Utah in grad school under Dr. Jim Steenberg. And I really found I liked the mountain meteorology aspect of things a lot. And it kind of, what I did at University of Utah kind of bridged synoptic meteorology with mountain meteorology. So then after I finished up there, I wanted to find something in clean energy, and I was able to talk UBC and BC Hydro into kind of a joint position where BC Hydro funds my position, but I'm employed by the University of British Columbia, and so I'll talk about our relationship a bit here. So it's what I would call a mutually beneficial partnership. So UBC provides research and forecasts to BC Hydro, and this is great because the graduate students are much cheaper than professional researchers, so they get a lot of bang for their buck, and we get to educate a lot of great students and on really good applied research type topics. So some of those topics are hydrometeorological forecasting for hydropower. So we provide temperature and precipitation forecasts to BC Hydro, and the hydrologists use that and plug that into their hydrology models and figure out the inflows to the reservoirs throughout the province. And then the planning engineers figure out kind of the optimal way to generate power across the province from those reservoirs. We also do wind forecasting for the wind farms. We have several wind farms in BC. And Dr. Sayuda there originally set up our wind forecast system, and that's still running today. And then there's a number of other related subjects that we also do research in, ranging from windstorms to electric load forecasting, and then of course high impact precipitation events like atmospheric rivers are very important as well. So some of the tools we employ at the university here, we have local and cloud-run mesoscale ensemble. We also download a variety of models from government centers, and then we post-process all this model information. We create forecast graphics, different forecast tools for a variety of partners that we have, and we also provide kind of raw forecast data for them. All right, so enough about that. We'll get into atmospheric rivers. So first question is, what is an atmospheric river and why do we care? So atmospheric rivers are long, narrow bands of moisture, and typically they're transported from north, or probably from south to north, but often they can also have quite an east-west component as well. I'm just gonna get that stuff, okay. All right. So they're responsible for about 90% of the meridional or south to north water vapor transport globally. And here on the west coast of the U.S. and Canada, they're also quite important because they're responsible for about 30 to 50% of our precipitation. And in some regions, like especially California in particular, they're pretty critical to the overall annual water supply there. But they can also be associated with quite extreme precipitation rates and totals, and have been known to cause $1 billion+ flooding events. So a quick geography 101 of BC. So we're just north of Washington State here. Vancouver, use the pointer here. Vancouver's down in the very far southwest portion of the province, and then just a bit north of there in the Coast Mountains is Whistler, and but the Coast Mountains are actually far more extensive than that. They run the whole length of the province along the coast. There's also mountains along Vancouver Island off the coast here. And then as you go down into the States, of course, these continue as the Cascade Range in the Northwest US, and then the Sierra down in California. So kind of the whole Western US has quite a formidable mountain barrier along the coast. So that's pretty important to atmospheric rivers, as I'll get into here. So we'll start off just taking a quick look at a case study from October 2003. This was the heaviest rainfall event in recorded history for British Columbia. And here in the satellite imagery, you can see a kind of the overall flow pattern here with moisture headed into the south coast of BC. A nice baroclinic leaf here. And this was our atmospheric river system. So this is a reservoir that's just south of Whistler. And you can see the dam here and the spillway gates, and then the actual intakes that go into the generation facility are elsewhere that you can't see out of this picture. So this is what a spill gate looks like when it's in use, but when there's the largest event in history, this is what the spillway gates look like when they're trying to get all the water out as quickly as they can so that the dam is not overtopped. So events like this really push the BC hydro system to the limits. And that's why forecasting these events is so critical, because if the engineers can anticipate in advance how much precipitation we're going to get, and then they can better plan and start, for example, lowering the reservoir ahead of time so that they can better handle these extreme precipitation rates. Here's another picture. This is from Rutherford Creek, just north of Whistler. And you can see the railroad track here not looking so good. And then this is actually Highway 99, which is no longer there. So that's kind of a major north-south route in British Columbia. That's another view of Highway 99 there. So as far as precip totals, this event was pretty impressive. 5-day precip totals were up to 18 inches, recorded at precip gauges anyway. This is for Squamish, which is halfway between Vancouver and Whistler. And Whistler, where a lot of those pictures were from that I just showed you, actually only got about 9 inches or so of rain. So there was double that amount in Squamish. And then other kind of the metropolitan areas ranging from, Vancouver here got about 7 inches. And then kind of a bit further west, a bit closer to the coast, within the Coast Range, the Ilaho Valley picked up 600 millimeters in 5 days. So that's 24 inches. So that's very impressive. That would be a lot of precipitation even for a hurricane. All right, so what is an atmospheric river? So as I said before, it's a relatively narrow, long band of water vapor transport. Typically, they're 400 to 600 kilometers wide, more than 2,000 kilometers long. And when we talk about them, often people use two terms, which we'll talk about here: integrated precipitable water and integrated vapor transport. So we'll go ahead and define those terms. So integrated precipitable water is the depth of water in a column of the atmosphere if all the water in that column were precipitated or condensed out as rainfall. So, and then it's measured as a depth in millimeters typically. This what is it? I can't actually see I forget what it's, there we go, XKCD comic. Kind of shows it here. So you have a bunch of clouds and rain all within a column of the atmosphere here. And if you were to just take all that, both liquid and vapor water, and condense it down to the bottom of the column here, then that's what you get is the integrated precipitable water. This water is it's not evenly distributed throughout the vertical extent of the troposphere. This figure shows here, if you just focus on the green line here, this shows for the mid-latitudes, a lot of basically the vast majority of the precip is in the lowest several kilometers of the atmosphere. So it's really the lower atmospheric water vapor that's really important, and the advection of that water vapor that's important, and what's happening at kind of the mid to upper levels of the troposphere doesn't matter that much. So the literature, at least some of the older literature, define an atmospheric river as having integrated precipitable water of greater than 20 millimeters and a length of greater than 2,000 kilometers and less than 1,000 kilometers wide. For strong ARs, we'll typically see more than 30 millimeters, sometimes even 50 or 60 millimeters for the highest IPW amounts that you would expect. So then integrated vapor transport is the advection of IPW basically by the wind. And this is measured in a nice non-intuitive unit, kilograms per meter per second. And so the literature here and the more recent literature prefers this integrated vapor transport for defining atmospheric rivers. And generally the threshold is 250 kilograms per meter per second. And for a strong AR, you would expect to see greater than 850 kilograms per meter per second. And this is the equation, which, yeah, I don't think well, I'll just go through it quickly, but basically it's just the specific humidity, the amount of water vapor advected by the wind, and then you integrate that from the surface up to 100 hectopascals. But as we said, it doesn't matter much how high you go once you get above kind of I don't know, probably around 500 hectopascals or so. So as I said, the earlier studies tended to use IPW, but for precipitation, of course, you guys know that you need both moisture and lift, and this integrated precipitable water alone doesn't really get at the lift part. So here at the West Coast, the lift is primarily produced by horizontal flow towards the mountain barrier, which is then forced up over the mountain barrier, and you get the condensing and raining out of the precipitation. So this IVT, the integrated vapor transport, is much more useful for diagnosing kind of the moisture flux across the barrier. In the eastern US, although IVT would be useful for kind of diagnosing the strength of the atmospheric river, as far as how much precipitation you guys get is not as related, is not as kind of closely tied to the orography as it is out here. So their frontal lift would play a much bigger role. So we'll talk a bit about different ways, different methods for detection and diagnostics of atmospheric rivers. But first we'll start with an aside, which is a little rant that I like to do about the misuse of water vapor satellite imagery. So this is just the two images on the left here. The top one is water vapor imagery, and this is basically just showing that water vapor imagery is not actually very useful at all for diagnosing water vapor in the atmosphere. So here you would from this water vapor imagery, you would probably surmise that this is the kind of wetter area right along the Gulf Coast here, and then down towards the Caribbean is much, much drier. But if you look at the integrated precipitable water in the atmosphere from the model at the same time, you can see that down in the Caribbean, we actually have really high IPW and IVT, and it's even higher than here along the Gulf Coast. So this is because the water vapor satellite imagery doesn't actually measure water vapor directly. Rather, it infers it from the infrared radiation that's absorbed and emitted by the water vapor. And it basically does this for the water vapor in the upper troposphere. And as we saw in previous slides, the water vapor in the upper troposphere doesn't matter that much. What really matters is the water vapor in the lower troposphere. So, and it's pretty useless for that. Water vapor imagery is useful for just generally looking at the upper level airflow. You can see kind of the large scale patterns, and it's good for comparing to upper level maps from models to see if they're picking up on all the different small and large scale circulation features. Okay, so things that are useful for looking at atmospheric rivers. So this is passive microwave imagery from the University of Wisconsin. And they basically take the passive microwave imagery and then combine it, with the kinematic fields from the GFS to advect the water vapor to create this kind of nice fluid motion that you see here. So this is great for looking at where the atmospheric rivers are and how they're evolving across the world. So this is, for example, this would be one here. Let's see here. So this one would be another one here, just north of Hawaii. So that's kind of what they look like in that imagery. As far as models, you can calculate integrated precipitable water and integrated vapor transport and plot them. This is one that UBC makes for BC Hydro. So the shading here is integrated precipitable water, and you can see the very large amount of integrated precipitable water down in the tropics and subtropics. That's kind of where think of it as like a precipitable water reservoir that then some of that precipitable water gets picked up into the mid-latitudes by these atmospheric rivers. And then so the arrows here indicate the integrated vapor transport. Yeah, so you can see pretty clearly here an atmospheric river going into Northern California. Other types of useful tools that have been developed, there's the Center for Western Weather and Water Extremes. It's at the Scripps Institute in San Diego, and they do a lot of work with atmospheric rivers. This particular model output shows the number of hours that atmospheric river conditions, which are defined as greater than 250 kilograms per meter per second, are expected at the various latitudes along the coast. And then this shows the probability of atmospheric river conditions being present at different latitudes and then through the forecast time. So you can see that in the first few days of the forecast period here, it's pretty much guaranteed that kind of the central part of the West Coast will be experiencing an atmospheric river. And this also takes advantage of ensembles to get at these probabilities. So ensembles can be useful for that sort of thing. Okay, so there's some terms that especially the media likes to use. One is tropical punch, and another is Pineapple Express. These are kind of pseudoscientific terms, but we'll talk about roughly what they mean. So the general types of West Coast atmospheric rivers, a weak river, you'd see a very narrow band of water vapor extending from the subtropics, and it just brushes the coastal areas with moderate rain for a day or two, so there's relatively little impact. And these types of systems occur frequently over a fall and winter season. Then a moderate AR event would feature a distinct band of water vapor extending from the subtropics near Hawaii, and it would impact some of the coastal and interior regions of BC with 2 or 3 days of moderate to heavy rain. And this can present a challenge for water managers and can cause some local flooding. And these types of events typically happen a few times over the cool season. So these types of events are what you might call a Pineapple Express. And then there are severe events, and these would feature an extensive band of water vapor extending from the deep tropics and impacting most of the coastal and interior regions of BC with 3 to 5 days of moderate to heavy rain. So this is potentially a disaster for water managers, basically more water than they can handle, and would cause catastrophic flooding. So events like this happen about once every 5 years. And so when you have an atmospheric river that taps into the tropics instead of just the subtropics, that's what they typically call a tropical punch. Okay, so now we'll take a look at the 3D structure of an atmospheric river. So one setup that you frequently see with atmospheric rivers is an amplified upper level trough with a large meridional extent. And this basically sets up a situation where you have air being advected from the subtropical latitudes, typically right near Hawaii for the west coast of the US, and then up into the mid-latitudes. And it's this large meridional extent of the trough that allows it to bring the air from those latitudes up relatively far north. Another possible setup is kind of a double trough structure. And if they're configured just right, you have the first one that does the initial transport of some of this air up from the subtropics, and then another one that picks up where that leaves off and brings it the remainder of the way up into the BC coast. So that's another possible setup. And then at the surface, this is a map that corresponds to that last upper level map that I showed you. So you can see kind of the double trough structure here with the initial advection and then the advection associated with the second trough bringing the bringing the water vapor into the coast. All right, so then taking a look at an 850 millibar map, or 850 hectopascals. Sometimes here in Canada we use even 85 kilopascals to keep the meteorologists confused. So this is what it looks like. You can see here in the temperature contours that we have a frontal zone that's basically overlaid on the atmospheric river. We have high relative humidities, that's the green shading here. And then we also have low-level convergence here at 850, and that helps to kind of reinforce the atmospheric river, and I'll get to that in a second. But basically, what you see with an atmospheric river at low levels is a cold frontal zone. And then as far as the results of that, here's a 5-day accumulated precip map, and this is actually for an atmospheric river that's forecasted to impact our area this weekend here in BC. You can see the date up here is is a forecast for the 5th of November. So the 5-day accumulated precip for the central coast of BC, here you can see in excess of 300 millimeters, and then here at the south coast, closer to about 150 millimeters is expected over that time period. So if we take a cross section, so here's a plan view kind of looking down from the top of atmospheric river. If we take a cross section across that, across the cold front / atmospheric river, this is what you see. So here's the cold frontal zone is outlined by these lines here. And then the specific humidity is in this dotted green line. So you can see the specific humidity is at a maximum just ahead of the cold frontal zone within the atmospheric river. And the wind speed is in blue. So you can see there's a low level jet here. In this case, it would be going into the screen. And that's also associated with the atmospheric river. And then the orange shading here indicates horizontal long front moisture flux. So basically an indication that we have, as we saw on the 850 map, lots of convergence. So you have lots of moisture convergence along the atmospheric river. So essentially you can see that an atmospheric river is basically the warm conveyor belt of which is kind of just ahead of the cold front within a typical mid-latitude system. So what makes a cold front with an atmospheric river different from other fronts? So probably the biggest difference is that it has a really extended or elongated tropical or subtropical feed. So it taps this really warm region with high capacity for moisture, and it's able to then, since it has such a long fetch, it's able to transport those high water vapor values northward. So this kind of presents an interesting situation for in the context of climate change. A few years ago, we had something that was known as the blob off the west coast, and it was basically an anomalously warm area of sea surface temperatures just off the coast here in the Gulf of Alaska. And we saw more westerly atmospheric river events that year. And I think what we're seeing happening here is that if the key is these really warm sea surface temperatures and warm atmosphere that these atmospheric rivers are tapping into, if our whole atmosphere is warming, and especially if we have these particularly anomalous high sea surface temperatures off the coast, then we don't necessarily need this very specific setup to get a really high flux of water vapor into the coast. It might be possible through more common kind of atmospheric setups. And so this is, blob. And then this year we have something that people are referring to, the son of blob, which is basically a less extreme version of the blob. So this is back from a few years ago when the original blob was in place, and this is a blog from Cliff Mass at the University of Washington, and he's talking about this westerly atmospheric river event coming into the BC coast. And then if we look at the forecast for this weekend, this is the so-called son of blob, sea surface temperature anomalies just off the coast. And I would imagine those are playing some role in kind of reinforcing the moisture flux along the last leg of the atmospheric river here. What's going on? Okay, there we go. Okay, so more on what makes ARs different from other fronts. So another component of this is very strong winds. So this contributes to the very strong moisture advection and temperature advection. And of course, the stronger the more moisture flux across the mountain barrier, the more orographic precipitation you're going to get. Another feature of atmospheric rivers is that since they come from such a warm area, they typically also bring pretty warm air mass into the coast. And so that's a big deal here for our mountain snowpack. So it first of all means that more of the precipitation with the event falls as rain instead of snow. And then secondarily, since rain is falling at a higher elevation than usual, you're likely to get rain on snow, which contributes even more to runoff. When precipitation falls as snow, BC Hydro doesn't typically care that much because snowfall doesn't really produce any runoff. So then the last component of what makes atmospheric rivers unique, especially more extreme ones, is that they can be very long in duration. So if we take a look at this animation with this red circle focused on the California coast, you can see that there are multiple waves. So if you think of basically the atmospheric river as being associated with a front, you get a setup sometimes where there are multiple waves along the front. And if those waves happen in a certain way, then one particular area of the coast gets hit repeatedly over a few or several days with an atmospheric river. Another way to think of it is kind of like a fire hose, just kind of like waving back and forth along the coast here. So obviously that produces really extreme precip totals, which makes it difficult for water managers to handle. And here's the kind of the cumulative impact of atmospheric river waving back and forth over a particular region for a few days. You can see totals here of up to over 300 millimeters. Okay, so now we'll talk a little bit about the climatology of atmospheric rivers. So this is a great study done by, I believe it was Colorado State University, 2016, and they well, basically this figure shows the frequency of AR type features. They came up with an automated atmospheric river detection algorithm, and then basically like counted the frequency over a long period of time. And so this is where AR features are most likely to occur or most frequently occur over the Pacific Ocean. And so you can see that kind of on average, these atmospheric river features tend to transport water vapor kind of from near southern Japan up towards the northeast, towards the west coast of the US. And if we look at the frequency as far as the seasonality of these atmospheric river events, atmospheric rivers in general, that's this gray line here, peak actually in the summer. You can see this July, August, September. And a lot of those atmospheric rivers are ones that come up out of the tropics and maybe don't hit landfall or are more restricted to the Central Pacific. And then landfalling atmospheric rivers for the west coast of North America actually peak in the winter. That's this blue line. So you can see them ramping up here in the fall and then ramping back down as we head into spring. Yeah, so that's just a bit about kind of the seasonality and seasonal distribution of these atmospheric rivers. Another study looked at frequency of atmospheric rivers along the west coast of the US here, and specifically in the November to February timeframe. And you can see that from November to February, they're most common basically from far southwest BC into Northern California. However, earlier in the season, atmospheric rivers are more common on the north coast of BC, like say in September, they're more common along the north coast of BC, the Alaska Panhandle, and even the Gulf of Alaska coast. This is another figure looking at the seasonality of them. So the different colorings indicate the month that atmospheric rivers are most common for that portion of the coast. So you can see that they're most common earlier in the winter, November, for the Pacific Northwest and Southwest BC, and then December for Central California. And then for Southern California, they're most common in January. So again, you can kind of see how they track southward as we get towards the heart of winter, which basically follows the jet stream, which also gradually goes southward as you go towards December and January. As far as contributions to West Coast precipitation, so this is looking at the percentage of precipitation that the West Coast receives that atmospheric rivers are responsible for. So it's at a maximum along the central and northern portions of the US coastline here, with about 50% of their total annual precip being provided by atmospheric rivers. So again, you can see how critical they are for a lot of portions of the US West. And then their contribution falls off pretty dramatically as you cross more and more mountain ranges heading into the interior of the Western US. So then, it's you know, a lot of the research and a lot of what I've talked about has focused on the West Coast of North America. That's where I am. That's just also where most of the atmospheric river research has occurred. But they're definitely not just a West Coast thing. This study from 2012 shows the global distribution of atmospheric rivers. I imagine that if you used a slightly different algorithm, you'd get even more. Notably, there's no atmospheric rivers indicated over the eastern U.S., but I would say that's not true. And I'll show a couple examples of that in just a minute here. So you can see that, you know, again, mostly they're transporting from the equator towards more poleward regions. And they also tend to follow kind of the storm track in the northern hemisphere from west to east. So here's an example of an East Coast atmospheric river event. So this was from Nashville, Tennessee in 2010. And there was a stalled cold front advecting lots of tropical and subtropical water vapor up from the Gulf of Mexico and the Caribbean. And Nashville received 493 millimeters in just 2 days. So quite a extreme event for them. Here's another example of an atmospheric river impacting the southeast U.S. You can see a low pressure system here centered over Mexico. And here's 3-day precipitation totals in excess of 20 inches for northern Louisiana. And here's the microwave imagery showing the integrated precipitable water plume coming up out of the Gulf into the southeast U.S. And then as far as other regions of the globe, they definitely affect Europe. This is an atmospheric river that's going into the UK here. And here's another example of an atmospheric river that's impacting Japan. Okay, so now I wanted to get into a bit about kind of the, I don't know, this is kind of the nitty gritty of atmospheric rivers, but looking at basically, is it a river? I think a lot of people have the impression that basically the water vapor is picked up in the tropics and then just dropped off on the West Coast. But that's actually not a very accurate picture of what's going on. So the typical lifetime of water vapor in the atmosphere is about 1 to 10 days, and within a frontal zone is typically can be a day or less, or up to a few days. And so many water vapor molecules, if you were to track the individual molecules, cycle through the frontal zone in atmospheric river as the atmospheric river is kind of gradually advecting this air mass to the north. So some of the moisture travels far and some doesn't. I'll talk about that a little bit more in the next slide. And then the last point on this slide is that what you see is a snapshot and in these maps that you're looking at. And so these fields are evolving over time. So if you see an atmospheric river at one time step going from Hawaii into California, that moisture is not instantly being transported during that time step. It might only move a very small distance along that path during that time step. And then the next time step, the atmospheric river might look different.
Hey, Greg,
so,
Greg, do you mind?
Yeah.
We just take a couple minute break because we were expecting pizza at the beginning of the seminar, but it just got delivered.
Sure, yeah.
Go ahead, get pizza.
Very spirited. Oh, nice. But yeah, thank you. Kind of went, what? You want pizza? What kind do you want? Cheese. All right. There you go. How are you doing? Fourth? Yeah, you want veggies? Yes. Cheese? Hope you guys don't mind me touching. I washed my hands at some point today, I promise.
Yeah. Oh, just a little bit. Thank you.
Yes, I do. Now follow me down to my house. Pepperoni?
It's the first in line. I'll go to it.
Yeah, because everyone's kind of like that. Jealous.
With a line start for 2 pieces.
I saw that. I went to breakfast with the rest Thank you, guys. Thanks, Greg.
Okay, Greg, sorry, thank you. Oh, now we can't hear you. Hold on.
All right. Is that good? Yeah. All right. I think I just have about 10 more minutes of stuff. All right. So, yeah, the whole concept of is it a river? So this study looked at where the water vapor that ended up in Norway here started out. And basically they found that the water vapor at the upper latitudes, or sorry, water vapor from the southern latitudes ended up in the upper levels, and then water vapor that ended up at the low levels in Norway was actually largely from local contributions from convergence of water vapor into the frontal zone. So there's a lot of moisture that's picked up locally over the ocean and converged into the frontal zone to maintain the atmospheric river. And this is another study from the west coast of the US that basically found the same thing, that a lot of the low level moisture comes from convergence into the frontal zone. So next we'll talk about predictability. And this is kind of like from a forecaster's perspective. So about 5 to 12 days out is when you can start to get an idea that there might be some sort of high impact atmospheric river on its way. And that's because there's some predictability in large scale patterns at this time scale. So as a forecaster, some of the things that we're looking out for are, is this a pattern that's capable of producing atmospheric rivers? Because a lot of times the planners are pretty happy if we can say, okay, well, there's a high pressure ridge next week. That means no chance of high precipitation rates or atmospheric river events. Whereas if we can't say that, then, it lets them at least, think about a plan of action if one were to occur. So for large scale type stuff, we look at ensemble 500 hectopascal maps. We also look at ensemble integrated vapor transport maps. So just to give you some examples, this is an ensemble 500 hectopascal map. And this shows the contours are the ensemble mean, and then the shading here is the spread amongst the members of the ensemble. So it kind of gives you an idea of the most likely weather pattern, and then also the uncertainty around that weather pattern. This is an ensemble integrated vapor transport map. And so this shows, again, the ensemble mean vapor transport in the arrows, and then the shading shows the spread in the ensemble. Kind of gives you an estimate of the uncertainty in the ensemble predictions. And then at the bottom here is an ensemble mediogram, and this allows us to look at precipitation totals for each day going forward, and see the distribution of the ensemble, which is in the shading there, and then the GFS and GEM deterministic model members are the orange and blue lines. So that kind of gives us an idea of where those deterministic models are falling in relation to the whole ensemble spread. Then at 4 to 7 days, we can start to get a better idea of what the kind of large scale frontal zone will look like, and its extent and strength. And to do this, you use a combination of ensemble and deterministic type tools. Again, the 500 hectopascal maps, integrated vapor transport maps like this one. And then we start to look at precip totals. Here's one from a couple of years ago, and I showed you the 5-day forecast, very similar map for this coming weekend for the atmospheric river that we're expecting. And then this one here is from that Western Institute for Water and Weather Extremes. And it shows integrated vapor transport indicated by the length of the vectors, and then the probability of reaching atmospheric river criteria in the shading there. And then once we get to 0 to 3 days, the short term, that's when we kind of want to fine tune the details of the forecast. So one of the biggest things is narrowing down the affected landfall area. For BC Hydro in particular, and this is also true for just metropolitan centers, they're relatively small areas, and kind of a positioning error of 200 kilometers or so can mean the difference between kind of a run-of-the-mill light precip event and potentially catastrophic precipitation event. So a study by Nardi et al. In 2018 found that in the 1 to 3 day range, you're looking at kind of a positional errors on the order of 100 to 600 kilometers. And there's also the gradient issue here, and this is kind of what I was getting at before. If this is our watershed outlined in red here, and then this is the kind of precipitation total gradient that we're dealing with, you can imagine that shifting this over 100 kilometers or so could mean a lot different precip totals for this map. So when you have gradients that are really strong, as you often do with atmospheric river events, that kind of amplifies any positional errors and the impacts of any positional errors. And then the other thing that they're looking at in this time frame is, are there additional waves along the front that might prolong its duration? Often models will miss kind of a smaller scale wave along the front that might give us an extra half a day of rain, which can mean a big difference in precipitation totals. And again, we're looking at ensemble and deterministic precipitation products. And then once you get within a day, you're also looking at the different satellite products and radar as well. All right, and then this figure just is also from that NARDI study, and it basically shows the predictability of atmospheric rivers. And you can see that they have some predictability out to about 7 days. And then the other thing that this figure shows is that you get about a day more predictability along the U.S. coast of the continental U.S. coast anyway, of California, Oregon, Washington, as compared to the BC and Alaska coastline, where forecast skill is substantially lower. All right, so the takeaway points from this talk are that atmospheric rivers are a primary source of water vapor transport and precipitation worldwide, and can be responsible for flooding events, and that's why they're so important to study. Integrated vapor transport is the best way to identify them and their strength. And heavy precipitation rates can result from this large moisture flux, the orographic lift, and then subsequent rainout across a mountain barrier. And if you get multiple waves along these frontal zones, then that can cause the atmospheric river to persist for multiple days, adding to the rainfall totals. And lastly, they're predictable on the scale of a few to several days in advance, and then pinpointing the area is often the challenge in the last day or so. All right, so that's all I had. I'll be happy to take any questions that you have.
Okay. So does anyone have any questions? Brad?
Yep. So I just have a question about the how much does ENSO, such as El Nino, La Nina, impact these atmospheric rivers, and what kind of correlation is there between them? Because I know, like in 1998 in California, they received a lot of rainfall because of El Nino. Now, so I just want to know the correlation between these two.
Yeah, that's a good question. So I don't know if I have any extra slides on this stuff. Yeah, so this study, I think again by Colorado State, they looked at relation to ENSO and to MJO, and let's see here. So the relation for different phases of ENSO as far as landfalling ARs on the west coast of North America was somewhat weak. There was a better correlation for the MJO, and they found that when the MJO was in phase 7 and 8, there's increased chances for landfalling atmospheric rivers. And you can see this kind of evidence for that here, where you can see a bit of a boost in the frequency for kind of the California coast in phase 7 of the MJO, and then more for the Northwest and for BC in phase 8 of the MJO.
Any other questions? I have a question. You talked about some of the locational forecast errors, but can you comment at all on how current models capture the magnitude of these events? Are there some errors there that you see commonly?
Let's see. I don't know of any. I don't know of any studies that have looked at that, and even from my own experience, I found that the magnitude varies widely. The magnitude of the error varies widely. Some events the models will handle quite well, and then there's definitely some events that we knew were going to be heavy precipitation events, but end up being more extreme precipitation events, where we'll forecast 130 millimeters for our weather stations on the North Shore Mountains here, and maybe they'll end up with like 220 millimeters. So you still do see models struggling a bit with that, and that could also be related to kind of the fine scale details of the terrain and how they're impacting precipitation that the models maybe aren't doing such a good job of capturing.
I think it was the timing of the pizza.
Yeah. All right, well, there's no other questions. I guess let's thank Greg again.
Great, thank you so much, Greg.
Welcome. Have a good day.
Grab more pizza on your way out.
Greg, do you have a, let me just stop recording.